A Hartnell Governor having a central sleeve spring and two right-angled bell crank levers moves between 290 rpm and 310 rpm for a sleeve lift of 15 mm. The sleeves arms and the board arms are 80 mm and 120 mm respectively. The levers are pivoted at 120 mm from the governor axis and the mass of each board is 2.5 kg. The board arms are parallel to the governor axis at the lowest equilibrium speed. Okay. Determine first the loads on the spring at the lowest and the highest equilibrium speeds and stiffness of the spring. So this is our question. Okay, we'll see how to solve it. Right. First, we'll write out the given data. Okay. First one, N1 is 290 rpm. Okay, because it's given. The Hartnell Governor having a central sleeve of spring and two right-angled bell crank levers moves between 290 rpm and 310 rpm. Right. So the minimum N1 290 rpm and maximum N2 310 rpm. So if the N is given, we can find the omega, right? So omega is equal to 2 pi n by 60. So 2 pi into 290 by 60, which will give you 30.4 rpm. Sorry, 30.4 radian per second. Okay. Similarly, for N2, that is 310 rpm. So to find omega, we'll write it as 2 pi n by 60. So 2 pi into 310 by 60, which will give you 32.5 radian per second. Okay. So N1 is given, N2 is given. Based on that, we found the omega 1 and omega 2. H is 15 millimeter. For a sleeve lift of 15 millimeter, right? So to find, between this RPM, the sleeve lift is 15 millimeter. That is 0.015 meter. And the ball arm, sleeve arm and ball arms are 80 and 120 millimeter respectively, right? So the sleeve arm is 80 millimeter and ball arm is 120 millimeter, right? So sleeve arm we know that is 80 millimeter Y and ball arm that is X 120 millimeter. Okay, and there's one more important data, right? The levers are pivoted at 120 millimeter from the governor axis and mass of each ball is 2.5 kg. Okay, so the levers are pivoted at 120 millimeter. Okay, so the pivot length R is equal to 120 millimeter. Mass of each ball is 2.5 kg. So we have two balls, each ball is 2.5 kg. The ball arms are parallel to the governor axis at the lowest equilibrium speed, right? So this is a notable data. The ball arms are parallel to the governor axis at the lowest equilibrium speed. So the lowest equilibrium speed is 290. At this speed, the ball arms are parallel to the governor axis, which means they won't tilt inside. What we have to determine the loads on the spring at the lowest and the highest equilibrium speed, right? We need to find the load on the spring. So which means S1 and S2 and stiffness of the spring, that is small s, right? So these are the data we have to find. Let S the spring load at lowest equilibrium speed and S2 spring load at highest equilibrium speed. Better we consider it as S1, right? There should be an S1. Since the ball arms are parallel to the governor axis at the lowest equilibrium speed, right? So which was a given data, the ball arms are parallel to the governor axis at the lowest equilibrium speed. Since they are parallel at the lowest equilibrium speed, so that is 290 rpm. If you take this figure, right? So they are parallel at the lowest rpm, which means their movement is from this position to this position. They won't tilt inside, something like this, right? So based on the question, we have to derive this concept, right? Otherwise, we cannot proceed with the question because we need to find some value first, right? We need to at least start from somewhere, right? So to start from somewhere, this data is important. The ball arms are parallel to the axis when the speed is minimum. Okay, right. So which means R is equal to R1, that is 120 millimeter. Okay, so we have already seen. Usually, what we take this at initial or mid position as R, inward tilt position as R1 for minimum, and outward tilt position as R2 for maximum. But here in this case, R and R1 are equal. Why? Because the mid position is the minimum position, right? So R is equal to R1, which is equal to 120. Okay, R is equal to R1 is equal to 120. So from this data, we can find the centrifugal force, right? By R is given, omega we have already found. So the centrifugal force Fc1 is equal to mr omega squared. M is also given, right? So we'll replace m omega 1 squared R1. So m is 2.5, right? The mass of the body is 2.5 kilogram. Omega 1 we have found that 30.4 rpm, 30.4 rad per second, right? 30.4 rad per second, omega squared into R1, which is 0.12 meter. Okay. So when you solve it, you will have Fc1 as 277 Newton. Okay. So the force at minimum position, we know that the centrifugal force at the minimum speed is 277 Newton. Okay. Now let us find the radius of rotation at the highest equilibrium speed. So we have found the lowest equilibrium speed. Okay. Now we have to find the highest equilibrium speed. For that, we need to first find the radius, right? Because here the radius is known. Why? Because it is given. But for the highest equilibrium speed, we have to find it. It's unknown. Okay. So now we'll write for the equation of the h, right? So h, previously we have found that h is equal to R2 minus R1 into y upon x, right? So y is given, x is given, R1 is given, R2 we have to find, h is given, so we can write. Okay. So when we replace these given terms with h is equal to R2 minus R1 in y upon x, we'll make R2 as the subject, right? Why? Because we need to find the R2. Or else you can have like this, and once after replacing it, you can make R2 as the subject, up to you, right? So I'll make R2 as a subject. R2 is equal to, right? R2 is equal to R1, right, into y upon plus h into y upon x, right? R2 is equal to R1 plus h into y upon x. Okay. So when we substitute R1, which is given, it's equal to 0.12. Right? R1 is given 0.12. Okay, 0.12 plus h sleeve lift, that is also given, h is equal to 0.015, right? H is equal to 0.015 into y upon x. Y is given how much? 80 millimeter, and x is given 120 millimeter, right? Okay, when we replace it, we will be having R2 is equal to 0.1425 meter. Okay, R2 is equal to 0.1425 meter. Okay. Centrifugal force at the maximum speed. So now we have found the R2. Okay, we have found the R2. Centrifugal force, we know the formula is Fc2, because we are finding at the maximum speed, right? Fc2 is equal to mr2 omega 2 squared, right? mr2 omega 2 squared. M is given 2.5 kilogram. Omega 2 we have already found, that is some 32.5 radian per second, right? That's omega 2. And R2 now we have found that 0.1425 meter, right? So M is given, omega we have already found, R2 we have now found, so we can replace them. So M 2.5 into omega 2 32.5 whole squared into R2, that is 0.1425 meter. So when you solve it, we'll be having 376 Newton, right? So force, centrifugal force at minimum position is 277 Newton, and centrifugal force at maximum position is 376 Newton. Okay. What was the question? Determine the loads on the spring at the lowest and the highest equilibrium speeds, that is S1 and S2, and stiffness of the spring, that is S. So now we have found the centrifugal force at minimum and centrifugal force at maximum positions, right? So Fc2 and Fc1 we have already found. So now we will move to the moment equation, right? We'll write the moment equation. So if you take moment about this point, which point we can consider is at point O, right? So mg plus S1, okay, neglecting the obliquity effect. So I already mentioned, if it is not given, to consider specifically either the weight of the ball or the arm length of arm changes. If it is not mentioned, you can simply neglect them, right? Simply neglect them. And after we neglect it, right, we found that this equation can be written as mg plus s1 equal to 2fc1 into x upon y. Okay, we have neglected the small mass, ball mass. Also, we have neglected this change in the x1, y1 things, right? So when you go to that step, so mg in plus x s1 into y equal to 2fc1 into x. As you can see here, mg plus s1 is equal to 2fc1 into x upon y. Okay, so I'll write this equation here. Mg plus s1 equal to 2fc1 into x upon y. Okay, so 2, right, 2 fc1 we have already found 277, right? fc1 we have already found 277. So 2 into 277 into x upon y. X was 0.12, y 0.08, right? X 0.12 and y 0.08. Okay, so if you replace all these terms, we will have s1 equal to 831. Okay, s1 is equal to 831. I'll come to this part. M is equal to 0. Okay, and for the highest position, mg plus s2 equal to 2fc2 into x upon y. Okay, so that's our equation. If we neglect the obliquity effect and the mass of the small balls, that is mg plus s2 equal to 2fc2 into x upon y, right? So mg plus s2 is equal to 2fc2 into x upon y. So mg plus s2 is equal to 2fc2 into fc2, that is centrifugal force at maximum, that is how much? 376 Newton. Okay, 376 Newton into x upon y. X we have found, not we have found, x already given 0.12 meter and y is given 0.08 meter. When you solve it, you will have 1128 Newton. Okay. So the highest position, the spring force is 1128 Newton. And why this m is 0? Because in the question, right, there was nothing mentioned about the m, right? Only the mass of the board is mentioned here, that is 2.5 kilogram, right? Mass of each board is 2.5 kilogram. But the mass about the central load of sleeve is not mentioned in the question, right? And therefore, this m is considered as 0, right? So this m is 0, this m is 0. So S1 is equal to this equation, and we have found it to be 831 Newton. And this is S2, which is found to be 1128 Newton. Okay, now we have to find the stiffness of the spring, and we know the stiffness of the spring is equal to SH is equal to S2 minus S1, right? That we have already seen previously, right? Stiffness of the spring S2 minus S1 is equal to H into S. So if I make S as a subject, S is equal to S2 minus S1 upon H, right? S2 minus S1 upon H. So small s is equal to S2 capital S1 capital upon H. So S2 we have already found 831. Sorry, this should be other way. This is S1 and this is S2, right? Because this is higher position, this is S2, and this is lowest position, this is S1. So here it's okay, S1, but here it should be S1 and this should be S2, right? So S2, that is 1128 minus S2, not S2, that is S1, 831 upon the H, right? So H, you can take 15 millimeter or 0.015 meter. Depending on how you write, you have to write this unit also, right? So here I made it as 15 millimeter because that's what given, right? So the sleeve list is 15 millimeter. So if you make it in 15 millimeter, you have to write the unit also in millimeter. If you write it as 0.015 meter, then you will be having around 19,800 Newton per meter. Okay. So when you solve it, you have 19.8 Newton per millimeter. Okay. So this S1 is correct, but here it should be S1 Okay, and this should be S2. Okay, this is S2 and this is S1. Just a printing mistake. Okay, so here is the stiffness of the spring. S2 minus S1, that is 1128 minus S1 831 upon H15, which will give you 19.8 Newton per meter. Okay,